Welcome to our exploration of electrostatic potential and capacitance. In this video, we'll break down these fundamental concepts in physics, making them easy to understand and relevant to everyday life. Electrostatics deals with stationary electric charges and the forces they exert. You might have experienced static electricity when rubbing a balloon on your hair or walking across a carpet and touching a doorknob. These simple experiences are rooted in the principles we'll discuss. Let's start by understanding what electrostatic potential means and why capacitance is so important in modern technology. Get ready for a journey through invisible forces that shape our world. Electrostatic potential is a measure of the potential energy per unit charge at a specific point in an electric field. Imagine placing a tiny test charge in the vicinity of another charged object. The work done to move this test charge from one point to another against the electric field defines the electrostatic potential difference. This concept is similar to gravitational potential energy, but instead of masses and gravity, we're dealing with charges and electric field. Understanding electrostatic potential helps us predict how charges will move and interact in various situations, from simple experiments to complex electronic devices. Grasp electrostatic potential. It's helpful to visualize electric fields. Electric fields are regions around charged objects where other charges experience a force. Picture lines radiating outward from a positive charge or converging toward a negative charge. The density of these lines indicates the field's strength. The closer the lines, the stronger the field. This visualization allows us to see how potential changes from one point to another. Electric field lines and equipotential surfaces are key tools for understanding how charges interact and how potential differences arise. Potential difference, often called voltage, is the work needed to move a unit charge from one point to another in an electric field. It's measured in volts. For example, a battery creates a potential difference between its terminals, causing charges to flow when connected in a circuit. This flow of charges is what powers our electronic devices. Understanding potential difference is crucial for analyzing circuits and predicting how energy is transferred in an electrical system. It's the driving force behind current and the foundation of electrical engineering. Electrostatic potential is measured in volts, named after the Italian physicist Alessandro Volta. 1 volt is defined as 1 joule of work per coulomb of charge. This unit helps us quantify how much energy is involved in moving charges within an electric field. In practical terms, household batteries typically provide 1.5 volts, while the outlets in your home supply much higher voltages. Understanding these units allows us to compare different sources of potential and design circuits that operate safely and efficiently. Whenever a charge moves in an electric field, work is done. This work can be stored as potential energy or converted into other forms, such as heat or light. For example, when you charge your phone, electrical energy is stored in the battery's chemical structure. The concept of work in electrostatics is closely tied to potential difference in energy conservation. By understanding how energy is transferred and stored, we can design better batteries, capacitors, and electronic devices. Capacitance is a property of a system that allows it to store electric charge. It's a measure of how much charge can be stored per unit potential difference. The most common example of a device that uses capacitance is the capacitor, found in nearly every electronic circuit. Capacitors store and release energy quickly, making them essential for smoothing out voltage fluctuations, filtering signals, and powering devices during brief interruption. Understanding capacitance is key to mastering modern electronics. Capacitor is a simple yet powerful electronic component. It consists of 2 conductive plates separated by an insulating material called a dielectric. When a voltage is applied across the plates, charges accumulate on each side, creating an electric field. The ability of the capacitor to store charge depends on the area of the plates, the distance between them, and the properties of the dielectric. Capacitors come in many shapes and sizes, each suited for specific applications in electronics. Capacitance of a capacitor is given by the formula C equals QV, where C is capacitance, Q is the charge stored, and V is the potential difference across the plates. The unit of capacitance is the farad, named after Michael Faraday. 1 farad is a huge amount of capacitance, and most practical capacitors are measured in microfarads or picofarads. This formula helps engineers design circuits that store and manage energy efficiently. Parallel plate capacitor is the simplest and most widely studied type of capacitor. It consists of 2 flat plates placed parallel to each other, separated by a dielectric. The capacitance increases with larger plate area and decreases with greater separation. The dielectric material also plays a crucial role, as different materials have different abilities to store electric energy. This basic design is the foundation for understanding more complex capacitors. Dielectric materials are insulators placed between the plates of a capacitor. They increase the capacitor's ability to store charge by reducing the electric field strength for a given charge. Common dielectrics include glass, ceramic, and plastic. The choice of dielectric affects the capacitor's performance, including its maximum voltage and stability. Engineers select dielectrics based on the specific needs of each application, balancing cost, size, and efficiency. When a capacitor is charged, it stores energy in the electric field between its plates. The energy stored is given by the formula E equals a half CV2, where C is the capacitance and V is the voltage. This stored energy can be released quickly, making capacitors useful in applications like camera flashes and power backup systems. Understanding how capacitors store and release energy is essential for designing efficient electronic devices. Capacitors are found in almost every electronic circuit. They can smooth out voltage fluctuations, filter unwanted signals, and store energy for later use. In power supplies, capacitors help maintain a steady voltage. In audio equipment, they filter out noise. Their versatility makes them indispensable in modern electronics, from smartphones to televisions and beyond. Capacitors can be connected in series or parallel to achieve different total capacitances. In series, the total capacitance decreases while in parallel it increases. This flexibility allows engineers to design circuits with precise energy storage and filtering capabilities. Understanding how to combine capacitors is a key skill in electronics and circuit design. One practical application of capacitors is in camera flashes. When you press the shutter button, the capacitor releases its stored energy in a split second, powering the flashbulb. This rapid release of energy produces a bright burst of light, capturing your photo perfectly. Without capacitors, such quick and powerful flashes would be impossible. Capacitors are also used for power backup in electronic devices. When the main power supply is interrupted, capacitors can provide enough energy to keep the device running for a short time. This is especially important in computers and medical equipment, where even a brief loss of power can cause problems. Capacitors ensure a smooth transition and protect sensitive data. In audio and communication systems, capacitors are used to filter signals. They can block certain frequencies while allowing others to pass, improving sound quality and reducing interference. This filtering capability is essential for radios, televisions, and mobile phones, ensuring clear and reliable communication. Electrostatic potential isn't just a laboratory concept, it's found everywhere in nature. Lightning is a dramatic example, where a huge potential difference builds up between clouds and the ground, eventually discharging as a powerful bolt. Even the static shock you feel after walking on carpet is a result of electrostatic potential differences. These natural phenomena remind us of the power and importance of electrostatics. From static cling in your laundry to the operation of touchscreens, electrostatics plays a role in our daily lives. Many modern technologies, such as photocopiers and air purifiers, rely on electrostatic principles to function. Understanding these concepts helps us appreciate the science behind everyday conveniences and innovations. Capacitors are increasingly important in renewable energy systems. They help manage the flow of electricity from solar panels and wind turbines, storing excess energy and releasing it when needed. This makes renewable energy sources more reliable and efficient, supporting the transition to a cleaner, greener future. Industries use electrostatic principles for painting, air filtration, and material separation. Electrostatic precipitators remove pollutants from factory emissions, while electrostatic painting ensures even coating of surfaces. These applications improve efficiency, reduce waste, and protect the environment, demonstrating the practical value of electrostatics. While electrostatics has many benefits, it can also pose hazards. Static electricity can ignite flammable gases or damage sensitive electronic components. That's why industries take precautions such as grounding equipment and using anti-static materials to prevent dangerous discharges. Safety measures are essential wherever electrostatic charges might accumulate. Electrostatic potential is measured using devices called voltmeters or electrometers. These instruments detect the potential difference between 2 points, allowing scientists and engineers to analyze electric fields and design better circuits. Accurate measurement is crucial for research, development, and troubleshooting in electronics. Capacitance is measured with a device called a capacitance meter. This tool applies a small voltage to a capacitor and measures the resulting charge. Knowing the capacitance helps engineers select the right components for each application, ensuring circuits function as intended and devices remain reliable. Electrostatic shielding is used to protect sensitive equipment from unwanted electric fields. By surrounding devices with conductive materials, we can block external fields and prevent interference. This technique is vital in laboratories, hospitals, and communication systems where precision and reliability are paramount. Capacitors help improve energy efficiency in power systems. They can correct power factor in electrical grids, reducing energy losses and lowering electricity costs. By storing and releasing energy as needed, capacitors make power delivery more stable and efficient, benefiting both consumers and utilities. Electric vehicles use capacitors to manage power delivery and support regenerative braking. When the vehicle slows down, capacitors store the recovered energy and release it during acceleration. This process increases efficiency and extends the vehicle's range, making electric cars more practical and environmentally friendly. Supercapacitors are advanced capacitors with extremely high capacitance. They can store and release energy much faster than traditional batteries, making them ideal for applications requiring quick bursts of power. Supercapacitors are used in electric vehicles, renewable energy systems, and backup power supplies, pushing the boundaries of what capacitors can do. Human body can accumulate static charge, especially in dry environments. This is why you sometimes feel a shock when touching metal objects. While usually harmless, static discharge can be uncomfortable or even dangerous in certain situations, such as around flammable materials or sensitive electronics. Awareness of electrostatics helps us stay safe in everyday life. Electrostatic principles are used in medical devices such as defibrillators and electrostatic air filters. Defibrillators deliver a controlled electric shock to restore normal heart rhythm, while air filters remove harmful particles from hospital environments. These applications save lives and improve patient care, showcasing the vital role of electrostatics in healthcare. Scientists use electrostatic potential and capacitance to study atomic and molecular structures. These concepts help explain chemical bonding, material properties, and biological processes. Research in electrostatics leads to new discoveries in physics, chemistry, and biology, driving innovation and expanding our understanding of the universe. Capacitors are essential in communication systems from radios to smartphones. They help tune circuits, filter signals, and store energy for transmission. Without capacitors, modern communication networks would be less reliable and efficient. Their role in connecting people and information is more important than ever. In audio systems, capacitors are used to separate different frequencies, ensuring clear sound reproduction. They block low frequencies in tweeters and high frequencies in woofers, creating a balanced audio experience. Capacitors are key to high-quality sound in speakers, headphones, and recording equipment. Capacitors are used in lighting systems to improve efficiency and reduce flicker. In fluorescent lamps, they help start the lamp and maintain steady light output. By managing voltage and current, capacitors ensure that lighting systems are reliable and energy efficient, brightening our homes and workplaces. Power supplies rely on capacitors to smooth out voltage and provide stable power to electronic devices. They absorb voltage spikes and fill in gaps when the supply fluctuates. This stability is crucial for computers, televisions, and other sensitive electronics, preventing malfunctions and extending device life. Capacitors are used in timing circuits to control how long a device stays on or off. By charging and discharging at predictable rates, they create delays and oscillations needed for clocks, alarms, and timers. Timing circuits are found in everything from microwave ovens to traffic lights. Many sensors use capacitors to detect changes in the environment. For example, touchscreens measure changes in capacitance when you touch the surface. This principle is also used in humidity and pressure sensors, making capacitors vital for modern sensing technology. Robots use capacitors to manage power and control movement. Capacitors provide quick bursts of energy for motors and sensors, enabling precise and efficient operation. As robotics technology advances, capacitors will play an even greater role in automation and artificial intelligence. Spacecraft and satellites rely on capacitors for power management and communication. In the harsh environment of space, capacitors ensure that systems remain stable and responsive. Their reliability and efficiency make them indispensable for exploring the final frontier. Smartphones, tablets, and wearable devices all use capacitors to manage power, filter signals, and enable touchscreens. As devices become smaller and more powerful, capacitors must also evolve to meet new demands. Their role in smart technology continues to grow with each innovation. Modern power grids that incorporate renewable energy sources depend on capacitors for stability and efficiency. By storing and releasing energy as needed, capacitors help balance supply and demand, making renewable grids more reliable and sustainable. Wireless charging systems use capacitors to transfer energy between coils without physical contact. Capacitors help tune the system for maximum efficiency, enabling convenient charging for phones, electric vehicles, and other devices. This technology is changing how we power our gadgets. Energy harvesting devices collect small amounts of energy from the environment, such as vibrations or light. Capacitors store this energy and release it when needed, powering sensors and low-energy electronics. This approach supports the development of self-powered devices and the Internet of Things. Emergency systems, such as alarms and backup lighting, rely on capacitors for quick energy delivery. When power fails, capacitors provide the necessary energy to activate alarms or keep lights on, ensuring safety and security in critical situations. We've covered the essentials of electrostatic potential and capacitance, exploring their definitions, formulas, and real-world applications. These concepts are at the heart of modern technology, powering everything from smartphones to renewable energy systems. As technology advances, our understanding and use of electrostatics and capacitance will continue to grow, opening new possibilities for innovation and sustainability. Thank you for joining us on this journey through the invisible world of electric forces.